Hello, and welcome to another episode of the Book Club, Computer Organization and Design. It might not be watchable live because of networking issues today, but it will be on the YouTube archive, so you can always tune in there if you are unable to watch it live. So before we jump back into the book, one thing I want to do is just give a little bit of a clarification to some of my explanation last time. Let me see here. Where were we when we were talking about that stuff? Oh yeah, I guess it was this stuff here. So the way I described it last time, I just think it was a little bit confusing. I described it as 2's complement being you add one conceptually, not actually, but to the the concept of the number you're representing. You add one and then you flip it, or you flip it first and then you subtract one. And I think that's a confusing explanation in retrospect. So I just want to clarify exactly what I mean by that. And by going through this, I think it's going to reveal some more intuition about the numbers as well. So basically, we have kind of this Platonic concept of like ideal forms. I think Plato. Let me just search this quick. Plato ideal forms. I'm no philosopher, but I'm pretty sure Plato, yeah, theory of forms or theory of ideas. This is what I'm talking about. So he had this idea of the idea of things, the idea of something, and then the reality of something, and that, for example, if you have the idea of a chair and then you have an actual physical chair that someone has made, the chair is just a model, a representation of the idea of a chair. It's it's an instantiation of that idea, and it's imperfect, right? It can never be perfect. Like, the idea of a chair is perfect, but the physical reality of a chair that someone makes is only kind of an approximation to that idea. That's kind of what he was getting at. And like I say, I'm no philosopher, but that's a little bit in this wheelhouse of what Plato was talking about way back in the day. And I think that's something that's worth bringing up, because this is something that we see a lot with computers, and a lot with what we're talking about right now with 2's complement. This whole idea of you have this mathematical, like, perfect ideal idea of what numbers are, right? And then you have the physical reality of what you need to implement. You have to make trade-offs. You have to have it be a finite subset, and as a result of that, it can't be a perfect representation of what numbers are in a mathematical sense. So I just thought I'd highlight that. And so let's start. We're going to start today by looking at just a number line of the the integers. And so you have, like, let's just start over here and count some some natural numbers. So and it goes on and on and on like this. And then if we start adding some negative numbers, they go over here. And it goes on and on and on like this. This goes all the way to plus infinity. This goes all the way to minus infinity over here. but in an actual computer, we have a finite, amount of space for holding a number, a representation of a number. So we can't do this, right? We can't. This is impossible to represent in a computer physically, right? So, for the onside numbers, what we do is we just say, let's start at 0 and count up to some fixed point. So for the sake of these examples, I'm going to use nibbles because 4 bits are easy to count off. So because you can represent them with a single hex digit, so you can count up like this, and then once we get here, and then what happens is, because this is the highest point we can represent for a 4-bit integer, what happens is we wrap around. So these are basically connected, right? It's a modular thing, because if you try to add 1 to f, it's going to roll over to 0 and then start counting up, and this pattern goes on for infinity, right? And then over here, the same exact thing is happening, where if you subtract 1 from 0, you roll over and you get f, and then it counts backwards, and it's a modular thing, is what I'm saying. It wraps around on itself. You can think of it as being like on a circle or a torus or something, right? It's a modular thing, and this is the range of what we're actually able to represent. So when we get to sign numbers, when we want to start representing these negative numbers over here, we have to ask ourselves, how are we going to fit those into this space that we have here? So if we have a 4-bit number, how are we going to represent negatives in that space? Well, what we can do is we can say, let's just start with the physical, representation here. So I'm going to write them in hexadecimal to save space, but you can think of these as the actual binary bit patterns that are in the machine, right? Because when I say 0 here, I mean 0, 0, 0, 0. When I say f here, I mean 1, 1, 1, 1, right? Just a more compact way to write it. And what we're going to do is we're going to need to assign some negative numbers to these different bit patterns, right? We're gonna decide how we want to map the numbers we want to represent onto the physical representations we have available to us. So the first thing we could do is we could say, well, let's see, we should be able to count up to, so I think what we would start at is like, if we just look at the number line that we started with here, up here, we could just say, well, let's just shift over where the 0 is and stick in the negative numbers, right? And I don't think anyone has ever done this as an actual representation of negative numbers in a computer, but it's a good place to start looking, right? So something like this, right? You could do something like this, and so these are the numbers that we're representing, and these are the actual bit patterns that we're using to represent those numbers. And what I've just drawn here is a perfectly valid representation, and in fact it has some nice properties, which is, you know, because these numbers are, you know, the negative numbers are counting up on the, you know, the number line in the same way that you would expect up here, and because the way this will wrap around, if you have 7, you know, which is the most positive number you can represent, and then you add 1 to it, you're going to wrap around to the most negative number. And if you subtract 1 from the most negative number, you're going to get the most positive number. So the modular behavior of this is good, right? And you can do addition and subtraction on this, and it's all going to work like you expect. So mathematically, you'd say the properties of this representation are quite good. The issue with this representation, of course, is that you know, you've shifted over where these numbers are. So your 0 now is represented as an 8 in hardware, and your 1 as a 9, and so on and so forth. So whenever you're doing something like comparing a signed and unsigned number, or you know, pretty much anything when you're working with signed numbers, you're going to have this problem where, like, oh, I want to check if something is equal to 0. Well, now you need to consider if you're doing a, you know, a signed number. 0 is no longer represented as 0 in hardware, so you're going to actually need to add on a constant, or subtract a constant, I guess, so that, you know, you'd have to subtract 8 from this so that 0 is actually 0. And there would be a lot of this would need to be done. It would be an extremely common thing that would have to happen, of adjusting by this constant, because the numbers are shifted by a constant, right? And so that's a lot of overhead that's not necessary. This isn't a good representation of negative numbers. But like I say, I think it's worth noting that it does have these nice properties of being able to do arithmetic on it like you'd expect, and the wraparound behavior being nice, and it only has one representation of 0. You know, it has some good properties, but like I say, all of these numbers, which you can also represent unsigned, now all of these have different representations. None of the representations match what you'd have, for example, as an unsigned number. So it's not so nice in that regard. That's kind of the trade-off we're making with this representation. Let's think of some other ways you can represent negative numbers, right? The other thing they talked about in the book on the last episode is you can do the kind of the most naive thing you could do is just saying, well, let's set one of the bits to be the sign bit, right? So if we have, you know, a 4-bit number, and let's say we're not going to do like 4 bits plus another bit for a sign bit. Let's just say one of the 4 bits is the sign bit, right? So let's start with doing like sign bit, and then these are your magnitude bits. And then we'll also look at the one where we do it like this, where we put the sign bit as the low bit. Well, because they said in the book that people actually tried both of those representations. So let's just look at it on the number line and see what that maps to, right? So what's going to happen is let's start again by drawing out the actual bit patterns we're working with here. Okay, and then so we're going to have 0 here, and these ones are all going to be the same. And then when we get to 8, this is the sign bit, so this is going to be -0, -1, -2, -3, -4, -5, -6, -7. Okay, so this is what the sign and magnitude representation with the high bit being the sign bit would be, right? And right away we see some nasty properties. First of all, here's a 0, here's a 0. we have two representations for 0, and we talked about why that's bad in the last episode. But notice the direction that the negative numbers are counting, right? Like the most negative is over here, and it's counting up going this way, right? We're approaching 0 going this way. Well, on a normal number line, your most negative is on this end, and you count up this way, right? So if you want to do arithmetic, when you're doing addition and subtraction, basically once you get to the sign numbers here, addition needs to be subtraction and subtraction needs to be addition, right? Like it's flipped because you're counting the wrong way on the number line. So this is why an adder would need to be different, right? Depending on the sign bit. Like the actual hardware would need to be different to support this because of the way this is represented, the way this is counting on the number line, where this is counting this way, and then once you get to the sign bit, it starts counting the other way. That's not how addition and subtraction work, right? So your hardware needs to special case for that. Your hardware needs to account for that. That's obviously a really bad, a bad way to go. So that's not a good representation. It loses the nice, arithmetic properties that we had in the first representation I showed you, where, if you're just talking about looking at a number line, this is like the most natural thing you would do, right? Where, you just, you count from the most negative to the most positive number using your, whatever patterns you have available to you, right? That's kind of, if you're coming from the approach of the number line, that seems like the most natural approach. Whereas if you're coming at it from kind of a hardware perspective, this seems like a more natural first approach, because it's like, well, we know how to do unsigned numbers, let's just add a sign bit, right? So that's kind of the naive thing that people first think of. But if you're looking at it more from a mathematical perspective, I think this is kind of the first thing you should think of. And it actually has nicer properties than this one, interestingly. So I don't know if something like this was ever actually tried, but what we'll see in a little bit is this is actually pretty close to what 2's complement is, right? But let's go through the other one first. So the other one is the other sign and magnitude representation, is where the sign bit is on the low end. And I actually haven't thought about this yet of what that means. So let's figure that out. So we're gonna have 0, 0, 0, 0, 0, 0, 0, 1. Oh, this is gonna be nasty. This is gonna be really nasty because I'll show you what I mean in a second. Because as we saw in the last episode, the problem we have here is whether a number is even or odd can be determined by the least significant bit. The least significant bit is flipping every other number when we count up on the number line. So I think it's kind of crazy that people would have even tried this representation. I guess they really kind of segregate the low bit as a special bit and have the adder just work on these bits here, because if you treated it as just, one thing, the adder would be really crazy. So what you have are these patterns here. So let's just start with these. So these are the actual numbers, right? These are the actual bit patterns we have in our machine if we have 4-bit integers. And again, I'm just doing 4-bit integers because it's easy to write out. I don't want to write out a ton of, this just makes it easier for me. But so the 0 pattern is just going to be 0. the one pattern is going to be -0, and then the next pattern is going to be 1, and then -1. Okay, so that's how it goes. So then it goes, 2, -2, 3, -3, 4, -4, 5, -5, 6, -6, 7, -7. So this is what it would look like if the low bit was the sign bit for the sign and magnitude representation. And this is even crazier, right? Like, I think the way you would need to work with this in hardware is you would treat the adder as working on just the the magnitude, right? And then you would just use the low bit to do the special casing in the same way that you would do it for the previous one we looked at. Because if you just literally did this, you have some big problems here, because this doesn't even, it's not even close to how a normal number line works. So your adder would be banana cakes, right? Like, that's just all around terrible. So the next thing we can do is, let me show you 2's complement, and then we'll do 1's complement. So the thing that you can notice about 2's complement is what you do is you say, here's our bit patterns again. And you have 0, 1, 2, 3, 4, 5, 6, 7. And now what you do is you do -8, -7, -6, -5, -4, -3, -2, -1. So you see, this is actually a pretty natural, going back to the first thing we talked about of how, what if you just, shift your window that you're looking at. Well, this is doing the same thing, where what we've done is, these are the negatives that we want to represent, and we've just chopped off the high end of the onside numbers and stuck the negatives right there, right? And the thing you'll notice about this is that the wraparound behavior right here is still good, right? I mean, this is literally exactly equivalent to the first representation we looked at, but it's just shifted because it's a modular representation. So if you understand the concept of that, this is basically living on like a circle, right? If you understand that it's modular, then it doesn't really matter where you start counting. You can have it anywhere, and what we've done with this is we've just lined it up so that the the positive numbers match their onside representation. They match what you have in the hardware, and that's really nice, right? That's some really nice properties right there. 0 is 0, these all match, and then you still have the nice wraparound behavior once you get to the sign bit. The most positive goes to the most negative, and the most negative wraps around to the most positive, and you'll see that once you get over here or over here, again, you have good wraparound behavior, because if you subtract 1 from 0, it goes to -1. If you add 1 to -1, it wraps around to 0, right? So the key idea there is, because it's modular, it doesn't matter where you start counting. If you do this, like, the wraparound will always work. And so this is actually the best way you have to represent numbers. It's pretty simple conceptually, right? We just stuck the negative numbers in over here, and it's the same as basically doing this representation here. We've just shifted it on the the number line, and it all works great. And so this is kind of what the book was stressing, is how they were saying how it's nice in hardware. It's like, well, you can see why it's nice in hardware, right? It's all counting the right direction, right? If we're counting up, this is all counting up this way, and this is all counting up this way, right? It's all counting the same direction. It has the nice wraparound behavior everywhere, and you know, it's just a solid representation all around. It has only 1 0. All of the positive signed integers match their unsigned counterparts. They match what the hardware representation is. Like, this is just great. And it's really conceptually simple if you look at it on a number line. I think that's kind of interesting to point out, that it's really as simple as this, right? It's really a very simple and straightforward representation. So now, if you look at one's complement, just for completeness sake, with one's complement, what you would have is this. And so the issue here is that it doesn't have the nice properties that this one has, in that we have a you know, 2 representations for 0, and the wraparound behavior is not so nice because you have -0 and 0 right next to each other on the number line. You have 7 and -7 right next to each other. You know, I mean, it's all counting the right direction, and this is, you know, most positive and most negative in the representation, so that's not that bad. But, you know, what really kills you is the 2 representations for 0. And, you know, it's just not as natural if you look at it from the perspective of the number line, like I just showed you. You know, these seem a little bit more natural than this does, because these representations are literally just taking the number line and, you know, putting it on the, you know, what you can, you're just mapping the number line to what you can represent. And this representation is just, it's modular, right? You've mapped it just like you did with this one, but it's just that it's shifted. It's a modular mapping, right? But that's still very natural. If you're comfortable with the modularity of it, it's still very natural. Whereas this one is not quite so natural, in that you've introduced this -0 and everything's a little bit wonky. But what I want to point out with this representation is what you've done is you've flipped, like, this is a mirror image, right? 7 and -7, 6, -6, 5, -5, 4, -4, 3, -3, 2, -2, 1, -1, 0, -0, right? It's a perfect mirror, where one half of the mirror is positive and the other half is negative, right? It's just perfectly reflected over the center of the number line. And now, with that in mind, with everything we just covered, all of this wasn't necessary to talk about what I'm going to talk about, but I wanted to point it out because there's some useful intuition in this, I think. So these are a bunch of different representations, and you can see how easy it is to kind of take different encodings and play with different encodings and see kind of how they shake out. It's quite nice, actually. And so my intuition that I was describing yesterday about the you know, flipping and adjusting by 1, I'm going to show you, you know, very rigorously what I was talking about. So here we have the representation again. And the reason I wanted to do this is because what I was saying in the beginning about Plato's ideal forms, I feel like my explanation is confusing because I'm kind of talking about the numbers we're trying to represent and not the numbers we actually that are actually in hardware, the bit patterns. So there's not good language. I don't have really good language to distinguish those two very clearly. And so I think it's more clear if I actually draw out the number lines for you guys. So what we're going to do is we're going to start by just doing unsigned numbers up to the point of reflection, right? So right here's the point of reflection, and here's the numbers we have. Now, if you do 2's complement, or 1's complement, as I just showed you up here, what you do is you just, you map these, you just flip them, you map them directly across the line here. You just reflect them. And when you reflect them, you're negating them, right, up here. Now, what you're doing with 2's complement is you can think of it as adding 1, not all the way across, but just these numbers here conceptually. You just add 1 to these. So this becomes 1, 2, 3, 4, 5, 6, 7, 8. Now you take these numbers up here and you do the flip, right? -8, -7, -6, -5, -4, -3, -2, -1. Right? It just you just flip those across after you added 1, right? This plus 1 gives you this, right? And then you just do the flip and you get these ones here. And so that's what I was talking about. And that's kind of a hand wavy operation. So that's why I think it was a confusing explanation. But you can see rigorously here what I was trying to get across is, you take these numbers, add 1 is these numbers, flip, here's these numbers, right? And the other way you can think about that is here's our numbers again. Let's draw the reflection line. Let's write the unsigned numbers on this side. Now, the other thing I said you can do is you can do the flip and then subtract 1. So let's do that. If we do the flip, you get the you get the 1's complement representation, and then we're subtracting 1 over here to the side we just flipped. So this becomes -8, -7, -6, -5, -4, -3, -2, -1, right? So -1 to get those, right? And see, we end up getting the same thing. That's what I was talking about. Those are kind of hand wavy operations, but that's kind of what I was thinking in my head, because I was thinking of it in terms of 1's complement and what we were talking about, and I was thinking about it in terms of the number line. And so this is kind of the explanation I came up with on the spot. And I don't think it's that good of an explanation, but now you can see exactly what I was talking about, right? But what you'll see is a kind of cleaner way to think about this, and what you do in hardware is if you have some number and you want to negate that number, how do you do it, right? Well, that is to say, you want to do the 2's complement operation on that number. That's what negation is. What is that operation? Well, it turns out it's actually just doing 1's complement to the number and then adding 1 to it. And that's kind of how I arrived at these ideas too. But what I'm doing up here, the reason it's kind of reversed from what you do in hardware is because what I'm talking about with hardware is you're doing that on these numbers, whereas what I was talking about yesterday, or not yesterday, but last episode, was doing it on these numbers up here, which are the kind of what the numbers you're trying to represent versus the actual bit patterns that you're working with, right? And so it should be pretty straightforward to see why, if you're working with these numbers down here, you know, if in these numbers up here what you do is you flip and then subtract one, it should be pretty straightforward to see that if you're working with these numbers down here, the same thing is to flip and then add one, right? So the idea here is, you know, if you have the number 1 and you want to say, okay, what is the number -1 in 2's complement? What you want to do is you want to go, you know, this plus some black box operation should take you to here, because that's -1, right? And similarly, if you say, okay, I want to know what -4 is, you know, you put 4 into this box, and out should come -4 over here, you know, right there. And you could also say, you know, let's take -8. Well, -8 you can't do. Let's take -6, put it into the box. It should spit out, you know, 6, and this box is just a 1's complement and then a +1, right? And it turns out that's really nice, as I showed in Risky Business, because if you look at the hardware here, for an adder, and this is what I drew when I did this on Risky Business, you can basically just have the B register. You can have a line coming in that controls whether it's add or subtract. So if the line is high, you know, if you send a voltage, you know, a signal down this line, then what the inverters are basically just a chain of exclusive ORs, where one input to the exclusive OR is the add or sub line, and then the other input to the exclusive OR is one of the lines from the register. So it acts as a conditional NOT. So if this is powered, it's going to invert the bits of all the bits of the register, right? So that gives you the 1's complement. And then you take this same line and you just put it into the carry in. It's pretty convenient that a full adder just so happens to have a carry in that can be used to add 1 to your result. So, you know, if you take the 1's complement of the B register and then you just add 1 in the full adder by using the carry in, well, that gives you the 2's complement of the B register. So what you're doing is the A register goes into your adder, the B register inverted goes into the other input of your adder, and then you're doing the adjustment by 1 through the carry in. That's equivalent to doing A minus B in 2's complement, because this is equivalent to doing 2's complement on the B register, right? So you don't really need to add much hardware. You know, you can use the same adder hardware to do both addition and subtraction, because it's really simple to just wire it up to be able to do 2's complement conditionally on one of the registers, basically. And so you see it's really nice in hardware. Do you have this kind of 2's complement representation too? And then also I want to mention that Per Vanten has been doing logic design on Bitwise, and he did a really nice episode. Well, all of them are really nice. He goes into a lot of advanced stuff quite quickly, but he did cover replicatory adders before doing more complicated stuff. And So I have a thread about this that, I just want to give a shout out. If you are enjoying this type of thing, check out Bitwise Day 50, Logic Design Part 2. He covers two's complement and ripple carry adders just like we did on day 12 of Risky Business and the last episode of Computer Organization and Design. But it's interesting. He covers it from the perspective of he wants to show you different circuits. So, for example, ripple carry adders were one of the circuits he wanted to cover, which he did in this episode. And then he ended up describing two's complement to explain that you could use the same circuit to do subtraction. But for him, it was kind of like two's complement was an afterthought for doing the ripple carry, whereas we approached it kind of from the opposite direction, where with Risky Business Day 12 what we were doing is we were looking at sign extension, and then that prompted us to look at two's complement, which prompted us to look at a ripple carry adder. So we kind of approached it from the different direction, and then with Computer Organization and Design, what we're doing right now, we've kind of approached it from a different angle yet of looking at the mathematics of two's complement, right? So all of these things kind of tie together, and I think it really gives a nice package. There's a bunch of different ways to look at this from a number of different sources. So I think we have a lot of good material kind of beating this topic to the ground. I think after this episode, one thing I'd like to do at some point is I'd like to do maybe kind of like a little lecture to, I want to do kind of, when I've mastered a subject like this, I want to maybe do a more compressed, condensed video, a short video rather than my long unscripted content that I usually do. I'd like to do some short videos. Also, hello, Croatia. I did see your message. Thank you for tuning in. But I'd like to do some shorter videos when I have a topic really mastered, just kind of as an educational thing, to say, okay, here's a topic that I understand. Here's a short video explaining that topic elegantly. And I think we're at the point now with this stuff that I could definitely do that. So I kind of want to script a short video to explain, unsigned numbers in binary, two's complement, all the intuitions we've developed about those things, and maybe looking at the hardware side of it too, of a ripple carry adder, because those things are all very well understood. And I think that would make a nice educational video for people. So that's kind of something I might do. But anyway, now that we've looked at all this number line stuff, let's jump back into the book. Oh, one other thing I want to say before we jump back into the book is another thing. I showed you guys my intuition of how you can count with zeros, and that basically works because you're doing the ones complement inversion, and if you're inverting the bits, basically the bits that hold value are inverted as well. So when you have a normal number, the ones represent, you want one of that place, you want value in that place, and a zero means an absence of value. You don't want any of that place in your number. So when you do an inversion, that dynamic flips, and the zeros represent value, and the ones represent an absence of value. So the zeros are kind of like the significant bits, and the ones are the zeros, so to speak. And so when you have a negative number, what this means is that this is useful in terms of sign extension, because if you look at a negative number, it has a bunch of leading ones, and then you have whatever your number is, right? And so you can use the topmost bit to determine what the sign is, right? That's your sign. But then these bits down here are the sign too, until you get to significant digits here. And this is intuitive if you understand the concept of the zeros being the ones that hold the value, right? These are just like zeros in an unsigned number. These don't hold any value, right? And that's why they're equivalent to the sign bit. And when you do sign extension, what you're doing is if you have a number that's like, some number of bits and you want to put it into, say, a larger register, like you have, I don't know, an 8-bit value that's a signed 8-bit number, and then you say, okay, I want to put it in a 64-bit register. Well, you're going to need to fill all those high bits, all the bits above the 8 bits of the original number. All of those are going to need to get filled with the sign bit. So if this bit is 1, then those are all going to need to get filled with 1s. But if it's 0, they're going to all need to get filled with 0s, right? And it's really intuitive to understand why that works. Again, thinking about it this way, that the zeros holds the value of a negative number, right? It's like, well, then of course you fill the high bits with 1s, right? And of course, if it's an unsigned number, they're going to be filled with 0s, right? It's a pretty straightforward thing. And it also is really useful if you're in practice, if you're programming and you want to look at the actual bits of a number. When you see a bunch of leading F's in hexadecimal, or a bunch of leading 1s in a binary, that can trigger in your mind, okay, this is a signed number, and you can look at, you can start looking at where the zeros are to kind of get an intuition of what number you're looking at pretty quickly, without like putting it through a calculator. So that intuition, I think, turns out to be a very incredibly useful one. So I just wanted to stress that and kind of connect it to sign extension, because that's something we're going to look at in the book today, I believe. So with that said, let's actually get back to the book finally. All right, so let's see, I think we left off, we're going to do these hardware-software interface sections. So let's see here. The previous page, we looked at the example of binary to decimal conversion. And I showed you guys how using that intuition that I just talked about made it very trivial to do it in my head. Now, moving on, we have the hardware-software interface section. It says, signed versus unsigned applies to loads as well as to arithmetic. The function of a signed load is to copy the sign repeatedly to fill the rest of the register. So yeah, that's what I was talking about just a little bit ago, sign extension, right? And I showed you kind of, why this is intuitive of, if you want to extend a number out this way, you're just going to fill it with the sign bit, because if it's a negative number, the 1s are equivalent to padding with 0s, basically. Whereas if it's an unsigned number, you literally pad with 0s, obviously. But it's intuitive why it works. If it's signed, why you'd fill it with 1s too, when you have that intuition developed. So they say that's called sign extension, but its purpose is to place a correct representation of the number within that register. Unsigned loads simply fill with 0s to the left of the data, since the number represented by the bit pattern is unsigned. When loading a 64-bit double word into a 64-bit register, the point is moot. Signed and unsigned loads are identical. risc-v does offer two flavors of byte loads. Load byte unsigned treats the byte as an unsigned number, and thus 0 extends to fill the leftmost bits of the register. while load byte works with signed integers. Since C programs almost always use bytes to represent characters rather than consider bytes as very short signed integers, LBU, which is the load byte unsigned instruction, is used practically exclusively for byte loads. All right, let's look at the next hardware-software interface section. Unlike the signed numbers discussed above, memory addresses naturally start at 0 and continue to the largest address. Put another way, negative addresses make no sense. Thus, programs want to deal sometimes with numbers that can be positive or negative, and sometimes with numbers that can be only positive. Some programming languages reflect this distinction. C, for example, names the former integers declared as long int in the program, and the latter unsigned integers, which are unsigned long int. Some C-style guides even recommend declaring the former as signed long int to keep the distinction clear. And I'd say that's nonsense. I don't know of any programs that do that, that explicitly write signed. I mean, if you do, whatever, it's fine. I mean, style doesn't really, it doesn't really matter, but in practice, it's pretty common to omit the signed keyword. You only use it in practice usually with characters, because the char keyword in C does not dictate whether it is signed or unsigned, whereas all the other types do. That one doesn't, and so if you want a signed one, you explicitly type signed in your program in C. But usually you just omit it. Anyway, let's examine two useful shortcuts when working with 2's complement numbers. The first shortcut is a quick way to negate a 2's complement binary number. Simply invert every 0 to 1 and every 1 to 0, then add 1 to the result. And yeah, I already discussed that. I think we've kind of beaten that to the ground at this point. This shortcut is based on the observation that the sum of a number and its inverted representation must be all ones, which represents -1, since x plus the negation of x equals -1. Therefore, x plus x inverted plus 1 equals 0, or not x plus 1 equals -x. So they kind of approach it from the mathematical perspective of how you can come to that realization algebraically, where basically you just say, you know that the sum of a number and its inverted number must be all ones, and you know in 2's complement that that's -1. So then you just do the algebra on that, and you see that it works out that x plus not x is equal to -1. So x not x plus 1 equals -x, right? They say we use the notation x with a bar on top of it, which is what I've been reading as not x, to mean invert every bit in x from 0 to 1 and vice versa. All right, so now we have an example. It says negation shortcut. Negate 2 base 10 and then check the result by negating -2 base 10. So I guess I'm confused here. They're saying negate 2 base 10 and then check the result by negating -2 base 10. So I guess they're saying just try the shortcut that they're talking about. So I don't think we really need to work through this, right? But you know, they're working with 64-bit numbers, but I'm just going to do a few of the low bits, right? So if you have the number 2 base 10, that's just going to be 1 0 base 2, right? And then you know, if you're going to let's just do a few leading zeros here. If you're going to do the negation of that, basically you just do, you know, the inversion. So you do 1 1 0 1, and then you add 1, so you get 1 1 1 0, right? And then the ones extend out quite far. So that's how you do that. And then they say, you know, start with representation of -2 and negate it and see that they match. So we're going to do 1 1 1 0, and we're going to negate it. You get 0 0 0 1, and then you add 1, so you're going to get 0 0 1 0, right? I don't think we really need to work problems like this because it's pretty obvious, and we've really covered this pretty heavily. So they yeah, they just write out 2 base 10 in base 2 as a 64-bit integer, and then they negate the number, and then they add 1 to the number, and of course they get all ones with the least significant bit set to 0, and then they say that's equal to -2 base 10. And then they go the other direction, so they start with all of them set to 1 except the least significant bit in base 2, and then they say that is first inverted and then incremented. So then they show all zeros with the least significant bit set to 1 plus 1, and then they say that's equal to, and then leading zeros up to 1 and then 0 in the least significant bit, and then they say that is equal to 2 base 10. Our next shortcut tells us how to convert a binary number represented in n bits to a number represented with more than n bits. The shortcut is to take the most significant bit from the smaller quantity, the sign bit, and replicate it to fill the new bits of the larger quantity. The old non-signed bits are simply copied into the right portion of the new double word. This shortcut is commonly called sign extension. And we have an example here. Sign extension shortcut. Convert 16-bit binary versions of 2 and -2 base 10 to 64-bit binary numbers. So they want us to do 16 bits to 64 bits. I don't think that's really necessary for us to do, but I guess for completeness sake, we'll push on through and do this. So they want us to do 2 base 10 sign extended to from 16 to 64. Let's just do like let's do 4 bits to 8 bits. How about that? We'll compromise. We're gonna do 4 bits to 8 bits. So 0 0 1 0 is 2, and then we need to put that into a an 8-bit number. So we're going to have the leading bits set to 0, and then the low bits are, you know, just the low bits. Now for -2, we're going to have the number 1 1 1 0 sign extended. So the, you know, this is just filling these bits up here are just taking the sign bit, right? And the same is happening here. So here's the sign bit. It gets, you know, copied into these bits, and then, you know, there's our number, right? That's how that works. So if we look in the book, the 16-bit binary version of the number 2 is, and they show 8 bits set to 0, and then the low 8 bits, it's just, zeros up until 1, 0. Then they say that is equal to 2 base 10. It is converted to a 64-bit number by making 48 copies of the value in the most significant bit, which is 0, and placing that in the left of the double word. The right part gets the old value. So you have 1, 2, 3, 4, 5, 6, 7 bytes that are all 0, and then the least significant byte is all zeros up until 1, 0 in the least significant bits. And they say that is equal to 2 base 10. All right, so let's look at their negative version. Let's negate the 16-bit version of 2 using the earlier shortcut. Thus, 0, 0, 0, 0. So, okay, well, it's 3 nibbles, 0, and then 0, 0, 1, 0, base 2 becomes all ones for a nibble 3 times, and then 1, 1, 0, 1 plus 1. So you get 3 nibbles that are all 1, and then the last nibble is 1, 1, 1, 0, base 2. Creating a 64-bit version of the negative number means copying the sign bit 48 times and placing it on the left. So you get 1, 2, 3, 4, 5, 6, 7 different bytes that are all set to every bit being 1, and then the last byte is 1, 1, 1, 1, 1, 1, 1, 0, base 2, which is equal to negative 2 base 10. Summary. Or, sorry, I'm skipping ahead of myself here. This trick works because positive 2's complement numbers really have an infinite number of zeros on the left, and negative 2's complement numbers have an infinite number of ones. The binary bit pattern representing a number hides leading bits to fit the width of the hardware. Sign extension simply restores some of them. Summary. The main point of this section is that we thought that we need to represent both positive and negative integers within a computer, and although there are pros and cons to any option, the unanimous choice since 1965 has been 2's complement. And I think we've really done a good job showing why 2's complement is the best choice. Elaboration. For signed decimal numbers, we used the negative sign to represent negative because there are no limits to the size of a decimal number. Given a fixed data size, binary and hexadecimal, see figure 2.4, bit strings can encode the sign. Therefore, we do not normally use plus or minus with binary or hexadecimal notation. What is the decimal? Okay, so here's a check yourself. What is the decimal value of the 64-bit 2's complement number? So it is all ones. It's 7 bytes that are all ones, and then the low byte is 1, 1, 1, 1. Let me see, did I count that right? 1, 1, 1, 1, 1, and then 0, 0, 0, base 2. So again, the way you do this is, you just count on your fingers. So it's going to be negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. Right, so the answer is negative 8. The options that give us for the answer are option 1, negative 4 base 10, option 2, negative 8 base 10, option 3, negative 16 base 10, option 4, 18, 446, 744, 073, 709, 551, 609 base 10. Obviously, it is number 2, negative 8 base 10. So let's look at the answers to the check yourself here. Answers to check yourself. 2.4, page 80. The answer is option 2, negative 8 base 10. So there you go. Then we have an elaboration. 2's complement gets its name from the rule that the unsigned sum of an n-bit number and its n-bit negative is 2 to the n. Hence, the negation or complement of a number x is 2 to the n minus x, or it's 2's complement. Let me just read that again, because I didn't know the origin of the name. 2's complement gets its name from the rule that the unsigned sum of an n-bit number and its n-bit negative is 2 to the n. Oh, okay. Hence, the negation or complement of a number x is 2 to the n minus x, or it's 2's complement. Makes sense, I guess. All right, next page here. So a third alternative representation to 2's complement in sign and magnitude is called 1's complement. Okay, so they do actually cover 1's complement. I thought they were just totally skipping over it, but I guess they cover it as an afterthought. The negative of a 1's complement is found by inverting each bit from 0 to 1 and from 1 to 0, or not x. This relation helps explain its name, since the complement of x is 2 to the n minus x minus 1. It was also an attempt to be a better solution than sign and magnitude, and several early scientific computers did use the notation. I believe I mentioned that in the previous episode as well. This representation is similar to 2's complement, except that it also has 2 zeros. There's the all 0 bit pattern, which is positive 0, and all 1 bit pattern, which is negative 0. The most negative number, 1, and then all zeros, represents negative 2,147,483,647, base 10, and so the positives and negatives are balanced. 1's complement adders did need an extra step to subtract a number, and hence 2's complement dominates today. A final notation, which we will look at when we discuss floating point in chapter 3. Ooh, we're going to get to floating point in chapter 3. That's going to be fun. Is to represent the most negative value by all zeros and the most positive values by all ones, with 0 typically having the value 1 and then all zeros. Oh wow, so I didn't think they were going to cover this notation, but that's what I started the episode with today. They're talking about this representation right here. I didn't know if this was ever actually used in computers. I didn't think it was. I just wanted to start the episode looking at this notation because I thought it was a good introduction to looking at these different encodings on a number line and how this relates to 2's complement. I thought that was like the obvious place to start doing this discussion that we had in the beginning of the episode. Apparently that's actually in the book here. I did not expect that at all. So they say a final notation, which we'll look at when we discuss floating point, is to represent the most negative by the 0-bit pattern and the most positive value by all ones, with 0 typically having the value 1 and then all zeros. This representation is called a biased notation, since it biases the number such that the number plus the bias has a non-negative representation. I did not know that. That's really interesting. So this representation that we started the episode with today is actually bias notation. Okay, so in the margins we have descriptions or definitions of 1's complement and bias notation. So let's just look over those quickly. 1's complement, a notation that represents the most negative value by 1 followed by all zeros and the most positive value by 0 followed by all ones, leaving an equal number of negatives and positives, but ending up with 2 zeros, 1 positive, which is the all zeros bit pattern, and 1 negative, which is the all ones bit pattern. The term is also used to mean the inversion of every bit in a pattern. 0 to 1, and 1 to 0. Bias notation is a notation that represents the most negative value by the all 0-bit pattern and the most positive value by the all 1-bit pattern, with 0 typically having the value 1 and then all zeros, thereby biasing the number such that the number plus the bias has a non-negative representation. So I guess the bias notation actually ties into floating point. I don't know. I guess I don't know off the top of my head how it ties into floating point, because floating point is like it has like sine and a mantissa and an exponent. I mean, I guess we'll see when we get to it how it ties in. I'm not an expert on floating point stuff by any means, but yeah, that's going to be really interesting to see how bias notation ties into floating point. I did not expect that at all. I did not expect it to have a name or anything. Like, I was just talking about bias notation from the perspective of like pure math, like just looking at the number line and like what's the most obvious way to represent both negative and positive numbers on, you know, the number line, you know. And it's like, well, you just take that window of what you can represent and stick it, you know, to the numbers you can represent. That's really interesting. I didn't expect that at all, so that makes me happy to see that actually ties into the book with bias notation, and that we're actually going to see that it has some relevance with floating point apparently. So something to look forward to there. That's the end of section 2.4. So we're going to end the episode here, and in the next episode we're going to do 2.5, representing instructions in the computer. So yeah, that's going to be nice to look at, and I'm looking forward now to chapter 3 when we get to floating point, not just because floating point, but because it apparently ties into what I talked about today with bias notation. So that's a fun surprise that we uncovered today. And then, like I say, I also want to do, before I end the episode, maybe let's just plan a little bit, because I want to do like I don't know what I'm going to call the series, but I want to do a series where I do short videos that are more prepared, and where it's, you know, me teaching something that I've mastered. And I feel like we've mastered, because this is pretty basics, you know, elementary stuff that we're doing right now in computer organization and design, like a ripple carry adder, and understanding how integers are represented is very basic stuff. And I think we've really, you know, mastered it, and we have a lot of good intuitions about it, and we could make a nice short video summarizing this stuff. So I kind of want to think, how should we, you know, structure that video? I feel like talking about this stuff, the different representations, is a good thing to go over. And we want to talk about the intuition of how flipping the zeros, counting with the zeros, as I call it, how zeros represent value in a negative number. We want to talk about, I guess, most significant bit and least significant bit, and how, like how the actual counting works. This stuff up here, the math of how bases work. I'd say that's probably the place to start. That's how computer organization and design started. So basically, I think the best way to treat this subject is to, in terms of teaching it, is you start with how do you represent numbers in base 10, because that's what everybody is used to, and then what that representation actually means mathematically, right, and how you can generalize that to any base, and then show how it works in base 2 like we did here. And then from there you have unsigned numbers, so then you say, okay, we have unsigned numbers, how would you do negative numbers, right? How would you represent a negative number? And then from there, what you would want to show is that I had a bit of an intuition that I talked about here too, so that would maybe be good to squeeze in when you're doing this stuff, mentioning how the high bit, how like numbers roll over, and the higher bit would be, you know, like 2 to the n minus 1. There's some intuition there. And yeah, from there, the thing to talk about, I think, would be, okay, we want to represent negative numbers, so let's draw out a number line and then say, here are some possible ways we could represent positive and negative numbers with the actual bit patterns and what it would be. And I think using nibbles is a good way to do that, because then you can just write it as hexadecimal. So you would want to cover, I didn't really explicitly cover hexadecimal today in computer organization and design, but I think in terms of an educational video, you should cover hexadecimal as well before you do this. But that would just take a second, right? So you do hexadecimal, and then you say, okay, here's the, you know, the different bit patterns, and here's the different ways you could represent these positive and negative numbers, and then talk about their pros and cons, and talk about what each representation is. This is bias notation. This one here is one's complement. This one here is, or no, this one is sign and magnitude with the high bit. This one is sign and magnitude with the low bit. This one is one's complement. Or no, this one's two's complement. This one's one's complement down here. So yeah, I'd show all these, label them, and talk about their pros and cons. And then from there, we see that two's complement is the best representation to go with. And I'd skip, I think this this intuition that I had here isn't useful, so I'd cut this stuff out of an explanation teaching it. But it was useful for us because this stuff here, which is what I considered to be kind of a bad explanation, which is why I was thinking about it. I was like, well, what did I mean rigorously by that? Like, how would I show what exactly I was talking about? And that got me thinking about, well, start with the number line. And then I thought, okay, well, if we start with the number line, we could do this. And that would be an interesting exercise to go through. And it turned out to be a very fruitful exercise to go through. So this was good that we thought of this, right? Because it led us down an interesting path that covered some good stuff. But in terms of an actual educational video, we could cut this out. We don't need to do any of this. We just skip straight to, you know, you do the representation, do one's complement, and then add 1 for the representation as a way to do the t's complement operation. And then we could end it talking about sign extension. And also, I guess I maybe want to wait to do an educational video on this until we've read the chapter 3 about floating points, because apparently bias notation is going to tie into that, and it would be nice to know how it ties into that, so that I can kind of give a hint of what's to come with floating point when we do an educational video of this stuff here, because we are going to talk about bias notation briefly. And if we're going to talk about bias notation, we should mention that that ties into floating point. So I think that's the plan with that. We're gonna do a video on integers after we've read chapter 3 of computer organization and design. And although the other thing I kind of forgot about, but the other thing is once we've seen how how 2's complement is the best representation, we would use that as the motivating thing to start saying, let's look at how do you do an adder. So then maybe that would be a separate video, I don't know, but we look at the truth tables just like I did in the risky business one, and use it to drive the ripple carry circuit, and then abstract that with a black box and show how you can chain them together, and then show how you have this carry in and say, okay, well, we know about 2's complement, we have an adder here. What if we want to do subtraction? Well, we know that a minus b is the same as a plus negative b. So what if we do 2's complement on the b register? And then, okay, how do you do that? We show, with exclusive OR, we look at how that can be a conditional not, and how you could just have a line going into cin and a bunch of exclusive ORs, and voila, right? So, and then that would kind of be emphasizing the point of why 2's complement is nice in hardware, to kind of tie it all together. So yeah, that's kind of what I'm thinking about, that I want to do some more condensed content, because not everyone likes the long form unscripted content that I do. It has an audience, which is nice to see, and I'm glad about that, but it would be nice to explore other avenues as well. So I kind of want to do that as well. But I only want to do educational videos, like properly teaching, if it's something that I really feel like I know to the core. And this is, this is what I know to the core in, integers. This is where we're at with that. But anyway, I hope you guys enjoyed this episode, and I'll see you guys in the next one. Thank you everyone who tuned in today, and thank you everyone who watches on the YouTube archive, which is available at risky.tv. And you can follow me at hmn_risky on Twitter to get updates about the series. For example, again today, just like the last episode, we had networking issues. So you can see that sort of thing on Twitter. I mention all that when things like that are happening and when this stream is delayed. So that's a good place to go to get updates, of what's going on. And thank you also to everyone who supports me on Patreon. It makes the series possible. I don't have any new shoutouts to give today, but I just want to stress that really makes a huge difference to what I do. It really makes this all possible. So thank you so much to everyone who supports me financially. And I will see you guys in the next episode. Thanks for watching, and stay risky.